March 2011. In mere hours, 20,000 lives were swept away and every existing barrier was shattered. Japan's $12 billion gamble, a 400-kilometer tsunami wall, was born out of that devastation, designed to stop what once seemed unstoppable. But can concrete and steel ever truly hold back nature's fury? Here is how radical engineering became Japan's last line of defense. Within weeks of the disaster, Japan's Ministry of Land, Infrastructure, Transport, and Tourism authorized an unprecedented public works program. A $12 billion budget was allocated, targeting nearly 400 kilometers of new seawalls and breakwaters along the battered northeast coast. Planners faced a daunting mandate: rebuild not just what had failed, but create a defensive barrier on a scale never attempted before. The coastline would be redrawn by concrete and steel, stretching from Aomori in the north to Fukushima in the south. Every town, harbor, and inlet was mapped, with engineers tasked to protect lives and infrastructure against the next tsunami. The financial commitment signaled a national resolve. This was not a temporary fix. It was a generational investment. Under the direction of MLYT, the project moved from policy to blueprint as teams of engineers and scientists began translating political will into technical plans. The challenge was clear: design a wall that could stand where others had not. Inside Japan's engineering laboratories, teams of civil engineers and university researchers began by recreating the forces that destroyed entire towns. Using massive indoor wave tanks, they generated scaled tsunamis and tested different wall geometries under controlled conditions. The data pointed to a trapezoidal cross-section, wider at the base and tapering as it rises, which proved far more stable against surging water than vertical designs. Reinforced steel cores threaded through the concrete gave each segment the strength to resist both the initial impact and the relentless pressure that follows. Final specifications called for walls reaching 14 to 15 meters in height, with foundations anchored as deep as 25 meters into the earth, well beyond the reach of ordinary storm surges. Every parameter was set by simulation: the angle of the wall slope, the thickness of the rebar, the density of the concrete mix. These blueprints would define the physical limits for construction crews, translating laboratory precision into the realities of a fractured coastline. Excavators and cranes arrived by the thousands, carving trenches along the battered coastline. Crews dug foundation pits up to 20 meters deep, each one a scar in the sand and clay. To keep seawater from flooding the sites, engineers erected massive cofferdams, temporary steel walls driven into the earth, forming dry islands where concrete could be poured in the shadow of the tides. The ground itself was a constant enemy. Sandy soils threatened to shift or collapse, so workers drove steel and concrete piles deep beneath every segment, anchoring the wall to bedrock wherever possible. Over 45,000 cubic meters of earth moved for every kilometer of new barrier. On the ocean side, teams stacked interlocking armor units, tetrapods, and massive concrete blocks, layer after layer, each designed to break the force of incoming waves before they reached the main wall. At the peak of construction, more than 30,000 workers and engineers pressed forward, pouring, shaping, and reinforcing the barrier day and night. The scale was unmatched, kilometer after kilometer of raw concrete and steel, transforming blueprints into a continuous, unbroken shield. At the heart of Japan's coastal defense, mobility and intelligence work hand in hand. Alongside the static wall, engineers designed a network of smart harbor gates, massive steel barriers that can seal off harbor entrances in minutes. Two main types operate along the coast: top-down gates, suspended from concrete towers, and bottom-up gates that lie hidden on the sea floor until needed. The entire process is triggered by Japan's seismic sensor network, which can provide up to a 20-minute warning after an offshore earthquake is detected. This window is critical not just for closing gates, but for moving ships, securing cargo, and starting evacuations. Gate engineering teams work to balance safety with the constant demands of commerce, ensuring ports remain open for trade and fishing until the last possible moment. The result is a dynamic layer of protection, responsive and automated, woven into the larger wall system. In the cold dawn, marine engineers guided colossal concrete segments, each weighing 73,000 tons and stretching 217 meters, out of their precast yards and onto waiting barges. Tugboats inched these giants through narrow harbors and out to sea, where teams worked in silence and radio code. Every segment had to be lowered into a dredged trench on the ocean floor, with divers and surveyors checking alignment to the millimeter. The operation demanded absolute precision because a single error could threaten the integrity of the entire chain. Underwater, the segments settled into place, locking together to form an unbroken barrier against the Pacific's force. Risk analysts reviewing simulation data found that the new seawalls can cut tsunami impact forces by 30 to 50%, a figure echoed by government reports. During the March 2022 earthquake off Fukushima, the system faced its first real-world challenge. While the resulting tsunami was minor, the defenses held. Residents remain divided. Some feel safer, others question the cost and the altered coastline. Today, concrete divides coast from sea, but absolute safety is an illusion. As climate extremes intensify, resilience demands more than walls. In the end, survival is a choice we must keep remaking.